This video is meant for Mrs. Rose's AB Calculus class, and it is on particle motion. Alright, the first thing you need to know is that S of t, or x of t, represents the position function. V of t represents the velocity function. It is the first derivative of the position function. And A of t represents the acceleration function. It is the first derivative of velocity and the second derivative of position. In word problems, they've got a lot of stuff, and the difficult part is deciphering what the question is asking. So you should use this list of when you see think to help you decipher what each question is asking. If they use the word initially or at the origin, you should think t is 0. If they use the word at rest, you should think that the velocity is 0 because it's resting, it's not moving anywhere. If the particle is moving right or forward or up, something positive, that means that the direction we're moving is positive, so velocity is greater than 0. And finally, if the particle is moving left or backwards or down, something negative, we say the velocity is less than 0. When you see an average velocity, we're just using average rate of change. So y2 minus y1 over x2 minus x1. So if we're doing average velocity, we're going to use s of b and s of a. I guess this is average on the interval from a to b. If you're looking for the instantaneous velocity at some time, you're going to take the velocity and plug in c. If you're looking for the acceleration at some time, you're going to take the acceleration, which is the derivative of velocity, which is the second derivative of position, and plug in c. If you're looking where velocity is increasing, you want to know where the acceleration is positive, and if you're looking at where the velocity is decreasing, we want to know where the velocity, the slope of velocity, or where acceleration is negative. If you're looking for speed, you should think the absolute value of velocity. If you're looking for where speed is increasing, you need to compare v of t and a of t. If v of t and a of t have the same sign, like both are positive or both are negative, then speed is increasing. However, speed is going to be decreasing if v of t and a of t have opposite signs. And finally, the particle is furthest right when you look for relative maxes. So you have to compare the position at endpoints in the relative extrema. The total distance traveled and net distance traveled, or displacement, and the position of an object at time t equals b will do at a later point. Alright, for our first example, the data in this table shows values for the velocity in meters per minute of a particle moving along the x-axis. The velocity is a differentiable function. Fix that. Function of time t. At t equals 0, is this particle moving right or left? So to figure this out, we're going to look at t equals 0, and the velocity is negative. Since the velocity at 0 is negative 3, we say that the particle is moving to the left because velocity is negative. Alright, on the interval from 0 to 12, we want to know if the particle is ever at rest. Well, we know that at 0, the velocity is negative 3, and we know at 2, the velocity is positive 2. Since the velocity is differentiable, it also has to be continuous, by the intermediate value theorem, and we are going from a positive to a negative, so we're changing sign, velocity is changing sign, the velocity function has to go through 0, meaning the particle has to be at rest sometime between t is 0 and t is 2. All right, for question 3, use this data from the table to find an approximation for v prime of 10 in terms of the motion of the particle. Make sure you show your computations to indicate units of measure. Well, we weren't given a value of the velocity at 10, but we were given values that were fairly close by. So what we're going to do is approximate the derivative using the average rate of change formula. Since t of 10 is not one of the times given the table, we're going to approximate the derivative of v of t by using the average rate of change between the best data available, between t is 8 and t is 12. So v prime of 10 is approximately v of 12 minus v of 8 over 12 minus 8. So 5 minus 7 over 4 is negative 2 over 4, which equals negative 1 over 2, and then the velocity is in meters per minute, and the time is in minutes. So our v prime of 10 is approximately negative 1/2 meters per minute squared. All right, now we're going to let a of t denote the acceleration of the particle at time t. Is there guaranteed to be a time where the acceleration is 0? Okay, well, we're going to go back up to our table. Since the velocity function is differentiable, it has to be continuous. And since v of 6 and v of 12 are the same, the velocity function fulfills all three requirements of Rolle's theorem. So we're going to say that it's yes, since velocity is differentiable on the interval, it also must be continuous on the same interval. And since v of 12 equals v of 6, also v of 12 equals v of 6, so by Rolle's theorem, there must exist a point in the interval such that the derivative of velocity, or acceleration, equals 0. Okay. For our next example, we're going to do an analytical one, and we are first asked if this function is moving right or left at t equals 0. Well, in order to be able to do that, we need to figure out if the velocity function is positive or negative. So we're going to need the velocity function. The derivative of position, or v of t, equals 3x squared minus 12x plus 9. And if you plug in a 0, 0 minus 0 plus 9 equals 9. So the particle is moving to the right since the velocity at 0 is positive. At t equals 1, is the velocity of the particle increasing or decreasing? Well, in order to figure out that, we're going to need to look at acceleration. So we're going to need to take the derivative of velocity, which is 6t minus 12, and we're going to plug in a 1. The acceleration at 1 is negative 6, so since the acceleration is negative, we say that the velocity is decreasing because acceleration is negative. Okay. For what values of t is the particle moving left? So we're going to go back to our velocity function, because moving left means that the velocity is negative. So I'm going to factor a 3 out of all three terms, and then factor the quadratic to get 3 times t minus 3 times t minus 1. Our critical values are 1 and 3. So if we do quick sign chart, we've got the intervals from 0 to 1, 1 to 3, and 3 to infinity. And plugging in 1/2, you get a positive velocity. Plugging in 2, you get a negative velocity. And plugging in 5 or 4 or 6 or whatever, you're going to get a positive velocity. So the particle is moving left for all values of t, where velocity is negative. The particle is moving left on the interval from 1 to 3 because the velocity is negative. For this last example, we're going to be looking at the graph of velocity on the interval from 0 to 9. And keeping in mind that velocity is the derivative of position. So this is also like saying x prime of t. Okay, at t equals 4, which is right here, is the particle moving to the right or left? Well, since the velocity is positive, it's literally above the x-axis, velocity is positive, so we're moving to the right. Okay. On what interval is the particle moving to the left? Well, what we're looking at is anywhere that the velocity function is negative. The particle is moving to the left on the interval from 5 to 9, since that's where velocity is negative. Okay. Back to t equals 4, is the acceleration of the particle positive or negative? Remember that acceleration is the slope of velocity, and the slope of this function of velocity right now, at 4, is negative. So, since acceleration is the slope of the velocity graph, and the slope of the velocity graph at 4 is negative, that means that our acceleration is negative. Okay. To find the average acceleration of the particle on the interval from 2 to 4, we're going to use the average rate of change formula. So I've got v of 4 minus v of 2 over 4 minus 2, which is 6 minus 9. So we got v of 4 is 6, v of 2 is 9 over 4 minus 2, which of course is negative 3 over 2. And in our units, we've got feet per second for the velocity and second for the time, so we've got negative 3/2 feet per second squared. All right, question 5. Is there guaranteed to be a time in the interval from 2 to 4 where the derivative of velocity, or acceleration, is guaranteed to be negative 3/2 feet per second squared? All right, this is basically a mean value theorem question. We've just shown that the average acceleration is negative 3.2, but the mean value theorem does not apply because at 3 we have a sharp corner. B of t is not differentiable. So no, even though the average acceleration is negative 3/2 feet per second squared on the interval, the mean value theorem does not apply. B of t is not differentiable at t equals 3. Last question, at what time in the given interval is the particle furthest to the right? Well, the particle is moving right when velocity is positive, so all of this, and the velocity is moving left when the particle is moving left when the velocity is negative. So if the particle is moving right until 5 and then it starts moving left after 5, it's furthest to the right at t equals 5. If you have any questions about particle motion, please feel free to stay after school or see me during Cavalier morning, and or shoot me an email.